So
perfect.
Here we go. So the talk is going to be organized as follows. We are going to have a brief introduction, setting a bit the ground on what we mean by IoT systems, and in particular, what are the challenges when we put a satellite in the picture of an IoT system. And then we're going to focus on a very specific challenge dealing with the communication system design, and deals on how we can organize the transmission of a large multitude of Internet of Things nodes, sharing the propagation medium towards the satellite. And then I will conclude and also provide some additional information about what we are doing in this context within our Munich Aerospace research group. Right before entering into the technical part of the proposal, I would like to spend a few words about our research group, which is together with TUM. So on the TUM side, we have Professor Gerhard Kramer and Professor Antonia Wachter-Zeh from the Institute of Communication Engineering. On the DLR side, the leaders of the activity are, besides myself, Dr. Hannes Barth and Dr. Andrea Munari. So the group was initiated with a slightly different configuration in 2017. And the scope was to address a subset of the challenges that are relevant to satellite IoT systems. And in particular, we were looking into efficient error correction mechanism for satellite IoT schemes, and as well in modulation. And that activity is fading out now, and we are starting since a few months a new activity that is dealing with other challenges that are relevant to this setup, which are how to handle the multiple access to the communication channel and how to address the need of security in the context of massive IoT satellite systems. I'm going to spend a few words about these topics in the next slides. Just to complete the description of our research group, I would like to take a few seconds to talk about the team itself. So within the research group, we had the possibility to finance 4 scholarships, so 4 PhD students. Delch and Mustafa, they started back in 2017, and they are now finishing their PhD. So they were part of the first line of research activities that we had within our research group. And we have 2 new scholarship holders, Anna and Human. Anna started already a few months back in 2021, and Human is going to start in the very next few months. So we need to sort out still some bureaucratic aspects to enroll him in our group, but he's going to start very soon. And look at the team at large. So from the TUM side, we have a big number of PhD students and researchers that are joining, I would say on a quite regular basis, our exchanges on the topics of interest for the research group that we have, as well on the DLR side, as you can see here. And we are happy also to include in a broad sense in our joint research activities also a number of international partners coming from renowned research groups around the world. And just to mention how also we like to do research together. And these pictures, as I was mentioning before at the beginning of this talk, now look a little bit like science fiction, but late February 2020, right before the big problem with the pandemic kicked in, we had the chance to have a joint workshop on the topics that are discussed in this presentation, together with organized together with MIT and the group of Professor Kramer at TUM. And we had more than 50 international guests. It was a pleasure to be all together, let's say, in a lecture room close to DLR. Unfortunately, this is not anymore so easy to do, but our hope is that soon, when the situation will improve, we will be in the position to keep organizing events of this kind, where the people of TUM and DLR, together with our international research partners, come together and discuss the most recent findings in the field that we are researching. So the goal of the research group is to develop communication information theoretic techniques for satellite short packet transmissions. What do I mean by short packet transmissions? I mean all those applications in which the communication happens by transmitting very little amount of information from every terminal towards the network. When this is the case, to come to the topic of today's lecture, well, this is the case in two classical scenarios that are becoming very popular nowadays. One is called Internet of Things, and the other is called machine-to-machine communications. What are these systems about? Internet of Things, we're going to see it later, is a setting in which we have a big number of devices equipped with transmitters and receivers, typically low power. And these devices want to exchange messages with other devices through the internet. And this happens frequently with the transmission of short data packets, so containing very few bits, maybe, I don't know, a reading of a temperature or a GPS position that is communicated over the network. The other setup that is quite closely related is the setup of machine-to-machine communications, where we may think of devices, even in industrial automation, that need to communicate with each other, so sensors that communicate with actuators that are placed somewhere remotely. So these are the settings we are interested in. And for these settings, in phase one, as I mentioned before, we looked at signal design with emphasis on error correction and efficient pulse shapes in order to handle well the small size of the packets that we are transmitting. And in phase two, we are addressing other two very fundamental problems: how to handle the access to the wireless medium, so in practice, how to manage the interference that is inherent to many of these systems, and how to build efficient low complexity encryption mechanisms that can work well on devices that have very limited computational capabilities. And the scope of this presentation is to focus on the medium access control problem. Okay, so I didn't mention it at the beginning, but of course, if you have any question at any point during the presentation, please feel free to interrupt me. I'm happy to take interactive approach to the talk. Otherwise, if you prefer to also ask questions at the end of the presentation, that's also fine. Okay, so let's enter a bit more in the IoT, Internet of Things problem. And let's try to understand what kind of devices or what kind of applications we have in mind when we think about the Internet of Things. So I took here a definition from Wikipedia, so where we have, I believe, a quite good description of what Internet of Things means. And as you can see, it basically describes physical objects that are embedded with sensors, transmitters, transceivers in general, processing ability, that enable these objects to connect and exchange data with other devices over the internet. Okay, so examples of such devices are, for instance, devices like smartwatches or smart home appliances like Google Nest thermostat here. Wireless sensor networks, even sensors that are present on vehicles, on cars, parking sensors, devices that are used to track containers in cargo shipping setups, monitoring of oil pipes in some remote regions. Anything of this kind fits well with the picture of IoT systems. And to understand how this market is evolving, I took from the 2021 Ericsson Mobility Report a chart that shows how many connections are expected to be present over the years in terms of IoT. And this chart reports the connections in billions. There are three types of IoT connections that are provided in this chart. I first give a look at the part that is here at the bottom. These are legacy 2G, 3G IoT connections. What does 2G, 3G means? This refers to the cellular network generation. Okay. Then on the top part, we have what are called broadband and IoT critical IoT systems that are typically handled nowadays with the 4G and 5G connectivity in cellular systems. And these are IoT connectivity setups in which we have, for instance, cameras which need to push a video over the internet, and they require hence a broadband connection. And then there is another, let's say, slice of this chart which deals with what are called massive IoT connections. And these are those I was referring to before. So those that relate to devices for health monitoring, for, let's say, smart home, smart cities, monitoring of oil pipes. And these are typically IoT scenarios in which there is no need of a broadband connectivity, because all those devices tend to transmit very little sensory data and very sporadically when they get active. And this type of, let's say, connections are growing much faster than the rest. And it is expected by 2027, they are going to represent the majority of the IoT connections in the cellular market. Now, the cellular market, the cellular communication paradigm is not the only one that can host IoT connectivity. There are many other systems that do not fall into the 3GPP standard umbrella that serve IoT systems. And examples are the long-range IoT systems that have been developed by some companies during the past 10 years. An example is Sigfox. Another example is the LoRa consortium. Amazon itself is deploying and developing a long-range IoT system that is meant to track the Alexa ecosystem that is proprietary of Amazon. And whereas, let's say, the whole IoT development done within 3GPP is done currently under the umbrella of the narrowband IoT, let's say, branding. Okay, what about satellites? Well, satellites provide an excellent match to some IoT applications. In particular, we all know that satellites have the nice capability of covering wide geographic areas, including remote areas where cellular connectivity is not present. And in the context of many of the systems that are currently deployed for IoT connectivity, the infrastructure turns out to be relatively cheap because many of the systems that are currently in development are based on the use of CubeSats. There are several companies that are emerging in the satellite domain, providing IoT services through relatively large constellations of CubeSats. Here I have a list of companies that just came up into my mind while preparing the slides, but I definitely know that there are many more that are starting to, let's say, operate and deploy their services. Something interesting, Swarm is a company that is using the LoRa, terrestrial LoRa waveform over satellite Swarm has been recently acquired by SpaceX, and just to, I want to mention this just also to mention the fact that currently many companies that are moving to the satellite domain are still using waveforms and protocols that are that have been designed for terrestrial communications. So they are definitely not well suited for communicating with satellites. Let's talk a bit what are the challenges that satellite systems have to face, especially in an IoT scenario. Well, we have to keep in mind the picture. The picture is, for instance, some very cheap node that is deployed in a remote area, battery powered. When the node is deployed, the position of the node is typically something that can change over time, maybe because the object to which the node is attached is moving. So in terms of propagation conditions, the situation is pretty bad. So we have the long distance to the LEO satellite. We have multipath because the antennas with which these devices are equipped are typically very simple multi-directional antennas. We have Doppler due to the movement of the satellites as well. The nodes themselves are very cheap in terms of hardware. They have small antennas, cheap amplifiers, limited signal processing capability because the computational complexity that can be afforded by these nodes is typically very small. And this comes also from the fact that these nodes are battery powered, they are deployed, and the operators don't want to change the battery too frequently. So they typically demand to have a lifetime of the sensors of the nodes of roughly 10 years. So there is a very strong requirement on energy efficiency, and the transmit power is, of course, something that has to be kept low. A big problem that we have and that this system have is that they need to handle massive populations of terminals. So a single satellite may need to serve something like 1,000 to 100,000 of users of terminals. These terminals transmit in an uncoordinated fashion, so it's very hard to coordinate the transmission of these terminals. And the behavior of the nodes is typically unpredictable and very sporadic. So again, you can think of a node that is attached to a container. The container is on a ship, and from time to time sends an update on the position of the container to the satellite. That's the type of behavior that we have in mind. So the problem of organizing the transmission over the wireless medium from many, let's say, objects to a common receiver, which is in our case the satellite, is a problem that is typically referred to as a medium access control problem. And medium access control protocols define how the access to the wireless communication medium is handled when we have a multitude of terminals. So if the terminal activity is predictable, then we can think of scheduling the access of our terminals to the wireless channel. And the classical ways to do that, very simple, are, for instance, to schedule the transmissions in time. So we allocate time slots to different users. Users know when they have to get active and transmit, and in this way we avoid creating interference among the terminals that we have in the network. And the same can be done in frequency, or if we are operating a CDMA network, we can also do it in the code domain. So the scenario in a let's say a coordinated multiple access system is then conceptually very simple. Terminals wake up, they transmit in the time slot that has been scheduled for them, and let's say no interference is generated among the different terminals. Now, the problem becomes, let's say, a bit more tricky when we have an extremely large population of terminals which act in an unpredictable manner. In this case, scheduling the activity becomes very inefficient, and because it would would entail a large delay and a low throughput. And this points to the need of efficient uncoordinated multiple access protocols. So when we think to the IoT networks we have in mind, the picture is more like this. We have a large multitude of terminals on ground. These terminals wake up and transmit in a sporadic, uncoordinated fashion. Okay, so this is the picture that we have to keep in mind. And the typical approach that is used when we have a situation like this is to resort to so-called random access protocols. In random access protocols, the idea is to let users transmit in an uncoordinated manner. So the focus next is going to move to random access protocols. Random access protocols and satellite communications have a long history together. So one of the first random access protocols that was ever developed was actually developed for a satellite network, the AlohaNet project set up at the University of Hawaii in the late 60s, early 70s. And the Aloha protocol was introduced by Norman Abramson exactly to solve the problem of multiple access from the ground terminals to the satellite. And it's a protocol that is extremely simple, and as all good simple ideas, it is widely adopted, and it's still very much in use. There are many variations that have been developed over the years of the Aloha protocol. There is a slotted version of the Aloha protocol where transmission is organized in time slots. There are variants of Aloha that use spread spectrum techniques on top of the protocol itself to simplify the separation of the users. There are protocols that exploit feedback to resolve collisions between users that are transmitting simultaneously in an efficient manner. For instance, contention tree algorithms. There is the carrier sense variant of the Aloha protocol, which is applicable when terminals can sense mutual transmissions. So there are really many variants of the Aloha protocol. So how the protocol looks like. Now going to spend just a few words about one of the simplest form of Aloha protocols, the slotted Aloha protocol, introduced by Roberts in 1975. So the idea is actually very basic. Time access is slotted, and the users transmit in a slot whenever they have a packet in their queue. So there is really no coordination taking place, and everything that happens on this channel is really random. It may happen that we have slots with multiple transmissions happening. In this case, we talk of a collision. Or we have slots in which no collision, no transmission takes place, and this we call them idle slots. Okay, so of course, idle slots are not good because they mean that we are not using the wireless medium efficiently. Collisions are also bad because when we have a collision, typically we lose all the packets that are involved in the collision. So under the slotted Aloha protocol, the typical assumption is that we are able to decode a packet only when the packet appears in a time slot without any interference, without collisions with other transmissions. Okay, so the behavior is really basic, can be summarized in let the terminals do what they want, right? That's more or less the principle. And if we want to characterize the performance of the slotted Aloha protocol, well, we need to define some very simple and important quantities. One is the load of the channel, which is the average number of transmissions per slot, how many packets per slot on average we have. The throughput is one of the figures of merit that we use to decide if the protocol is working well or not. And it's basically the average number of packets that we can decode per slot. Another important figure of merit is the packet loss probability, which is the probability that a packet that is transmitted is not correctly decoded at the destination. In the analysis of the slotted Aloha protocol, a typical assumption that is made is to assume that in presence of a collision, all the packets that are involved in the collision become undecodable. So only singleton slots, so slots with only one packet transmission, contribute to the throughput. So they contribute to the calculation of the number of packets that can be decoded. So actually the throughput is exactly the probability that a slot is a singleton, so a slot sees only one transmission. And when the terminal population is large, well, it is quite easy to show that the throughput can be expressed as a function of the load with this simple expression. So we have lambda, the load, times the exponential of minus lambda. And the packet loss probability takes also a very simple form, is 1 minus exponential of minus lambda. So let's plot these two functions. So here we see the throughput in packets per slot over the load in packets per slot. And the peak throughput is achieved when the load is set to 1 packet per slot on average. And the load is, the throughput, the maximum throughput is roughly, in this case, 36, 37 packets per slot. Okay. The figure for the packet error probability is here. That's a little bit more dramatic in the sense that if we want to have a very low packet error probability from our simple slotted alloy protocol, say 10 to the minus 2, which means 1% of the packets get lost, well, we need to operate an extremely low load. Okay, so we need to operate really with a load close to 0. And that points, in fact, to the weaknesses that are inherent to such simple protocols. Protocols that I mentioned before are, maybe with some adaptations, still widely used. So they are the main medium access control protocol of terrestrial long-range IoT systems like LoRa and Sigfox. They are used in satellite communications, for instance, by the DVB RCS standard, which is the standard for interactive satellite communications for initial logon. And it's also the random access channel that has been standardized by 3GPP for third generation, fourth generation, and the last fifth generation cellular standard. The main limitation, as I mentioned before, are poor throughput and the packet loss probability that is, let's say, puts a very strong requirement on the load that the system can sustain. So the peak throughput is only 36%, and the maximum load that we can put on the system in order to achieve a maximum packet error rate of 10 to the minus 2 is roughly 1%. So we need to operate the system with an extremely low load. Okay, so here comes what has been done more recently on the problem, and exactly because of the need that IoT systems have of a highly efficient uncoordinated multiple access protocol, there was during the past, I would say 10, 12 years, a lot of research ongoing in developing more performant random access protocols. So the basic protocols like ALOA, slotted ALOA, are definitely not suited for, let's say, delivering high performance in the context of large-scale IoT systems. And as I mentioned before, during the past 15 years, there have been definitely some big step forward in research regarding the development of advanced random access techniques. So example of approaches are listed here. For sake of time, I will skip going through the entire list. I'm going to speak only about a variant of such modern random access protocols on which we have been working a lot during the past. And I would like just to mention that all the schemes that are mentioned here have as key ingredients the use of advanced signal processing techniques, use of multi-user detection and successive interference cancellation to handle the mutual interference that all the nodes that we have in the network may cause on each other. So let's see what is the basic idea of one of these modern random access protocols. The transmission is organized in a frame, and a frame is composed by many slots. In this example, we have 7 slots. And let's assume that we have 4 users that become active during this frame. So each user picks basically 2 slots at random and transmits 2 copies of its packet in the 2 slots that have been chosen. And every user does the same. Okay. So now, what do we do at the receiver side? At the receiver side, we seek for slots where there is only 1 packet present. For example, on slot 1, we have only the packet of user 3. We decode it, and then we find out where the copy of this packet has been transmitted, and we physically cancel the interference contribution that this packet caused on the corresponding slot. So basically, our receiver is storing samples of the received signal. As soon as we decode a packet in a given slot, we go in the corresponding slot in our buffer of samples, and we remove from those samples the contribution of interference caused by the user that we just decoded. And by doing that, we may unlock other slots where we see now only a single transmission. And we repeat this process iteratively over and over again. And if we're lucky, we are capable of resolving, so of decoding all the transmissions that took place over the frame. Okay. So a way to analyze this protocol is to make some assumptions. So we assume that in presence of interference, again, we cannot decode. With no interference, instead, we succeed in the decoding. And we assume also that interference cancellation is done fairly well. So we can neglect the residual interference contribution that we can have due to the imperfectness of the interference cancellation process. And again, we need to define properly the load, which is average number of users over number of slots that we have in the frame. And the throughput is the average number of decoded users per slot. And if we look to the picture of the throughput versus load with respect to the slotted Aloha protocol, we see that already with a very basic design of the system, so 3 repetitions, we are able to almost double the throughput that we can deliver. And if we look to the packet loss probability, the figure is even nicer. Now, remember that for slotted Aloha, to achieve 10 to the minus 2, so 1% packet error probability, the load of the system cannot exceed 1%. Well, with 3 repetitions and the protocol we just described, we are capable of sustaining roughly a load of 0.7. So this is a 70-fold gain with respect to the conventional slotted Aloha protocol. One interesting thing of this class of protocols is that they admit also a graphical representation. So we can represent a frame using a bipartite graph where we have a node for every active user and another type of node for every slot in the system. And we draw edges between nodes on the left and node on the right, depending on where we place our transmissions. And we can track the iterative interference cancellation process through the graph on the right and describe this as an edge peeling process. Edge peeling processes have been widely studied in coding theory, and there are many, many tools that we can borrow from coding theory which allow us to, let's say, optimize the construction of our random access protocol. And so thanks to the use of these tools, which basically treat the edge peeling process as an exchange of information between the nodes that we have on the left and the nodes that we have on the right of our graph, well, we can characterize how the interference cancellation process evolves iteration after iteration. And thanks to this, for instance, we are able to achieve designs which deliver basically a vanishing small, so very small packet error probability at loads that are close to 1 packet per slot. Okay, that's in a way the best that you can hope for. So decoding 1 packet per slot is what we would have if we would apply a TDMA coordinated approach. And here we get it without coordination. So this kind of protocols has been standardized in the update of the DVB-RCS standard, so DVB-RCS2, and variations are currently considered for adoptions in a few satellite IoT systems. The main limitation of this protocol, which I didn't discuss here, but it's somehow intuitive, is that the scheme is not energy efficient. So the fact that whenever we wish to transmit a packet, we transmit copies of it, means that our device is consuming some extra energy to handle those transmission replicas, right? And so, especially thanks to some recent information theoretic work that has been done on this setting, we will be able to check how much is the energy inefficiency with respect to theoretical bounds, and we observed that protocols of this kind still pay a gap to the theoretical bounds in the order of 2 or 3 dB. Okay, so there is a 2-3 dB gain that can still be achieved. In the sense of energy efficiency, they can be in fact outperformed by more complex schemes based on compressive sensing, which nevertheless have extremely strong requirements in terms of user synchronization in time and frequency, which renders them in a way hard to apply to practical satellite systems. Still, the approach that I just described, together with a spread spectrum variant of the Allow protocol, represents a solution that is quite appealing for systems that have limited synchronization capability, and therefore are currently the only options available in satellite IoT systems, given the fact that the more complex systems based on compressive sensing suffer from too strong requirements. Okay, so I'm ready to conclude the talk. The big, let's say, developments that are happening in the IoT domain are responsible also of rapid developments that are happening in the area of satellite communications. There are already a number of proprietary, moderate size, or even large LEO satellite constellations that are deployed to serve IoT applications over wide geographical areas. The companies that I mentioned at some point during my presentation, they all have access to their, let's say, satellite constellation for delivering the IoT service. Most of those systems still are based on terrestrial long-range IoT waveforms and on basic MAC policies, medium access control policies. And that's totally fine as soon as the load on their system is low. But if their system will start to gain, let's say, widespread acceptance and more terminals will start to populate the network, I believe that they will need to look into more sophisticated medium access control policies, eventually giving an eye to modern random access protocols. And so modern random access protocols are a key to support a massively large population of terminals. And we believe that going in this direction is something that has to be done to, let's say, scale up the population supported by those systems. And despite the progress that has been done during the past years in coming up on with improvements to the basic Allow protocol, there is still large space to get gains. So what we are doing within our research group currently is exactly this. So to design new random access schemes for satellite IoT systems with a strong focus on energy efficiency, which is currently not well, let's say, served by even the most advanced protocols that have been developed. We are also looking into the schemes that we build from perspectives that go beyond the pure throughput or packet loss rate, let's say, point of view. We are looking into performance metrics that take into account the nature of the traffic, like age of information, which keeps track of how frequently updates of a given, let's say, sensing device are delivered, or distortion metrics like, for instance, mean square error when we are trying to estimate remotely, for instance, physical quantities that vary on the field. We're also developing encryption methods that are tailored for the low computational capabilities of IoT nodes. And in particular, we are looking into quantum-resistant lightweight crypto systems, based, for instance, on the McAleese code-based approach or on lattices. So that's it from my side. I hope I was not exceeding too much the time that was allocated. I would like to thank the whole Munich Aerospace team. I would like to thank you all for listening. I appended to my slides a bit of bibliography on recent works on advanced medium access control protocols for satellite IoT systems. So thanks again, and I'm ready to take questions.